Well, I find myself fundamentally in sympathy with the last speaker and share the same excitement for a post-fossil fuel world. And that's going to be part of what I'm talking about to you today. And before I get started on it, I want to give you a visual image so that you know what the idea is I'm talking about, because comparatively few people are familiar with this concept. So what you're seeing here is a depiction of a space solar power satellite. Basically, it's some 7 kilometers across with a transmitting aperture of about 1 kilometer across. In this particular incarnation, these are primary, very, very low density mirrors that focus it on secondary mirrors. These are photovoltaic cells on top, concentrator in this particular design. Then there'd be a phased array antenna on the bottom that's beaming it down in microwaves, probably in the 2.45 to 5.8 gigahertz. This would be about the size of a municipal airfield, the series of, it's a rectenna array, and then it would go from that into a city. So that's sort of a grand overall vision, and now I'm going to talk a little bit about why somebody would even consider such an outlandish idea. Now, I came to the energy field probably from a different area than most of you did. I'm a defense security thinker, and it's important I preface this talk that this is purely my opinion, and while I'm sponsored by the Council on Foreign Relations and work at the IDSA, what I'm presenting here doesn't represent a point of view of any of them or the U.S. government, though I am a U.S. government employee. In my last job, I was at the Pentagon. I was supposed to be looking very long-term, 20 to 50 years out in the future. What would be the stressors? What would be the possible causes for conflict? What could we do to avert them? What are revolutionary technologies? I was basically sort of the Air Force's chief futurist and tech scout for the headquarters. And so I began, climate change, energy became concerns of mine, as did possible solutions. Most of the solutions I think you already know. I want to tell you about one that I don't think very many people know about. So as you know, the world desperately needs energy options for development, and it really needs options that can deliver terawatts of green energy. We're somewhere on the order of 15 terawatts today, looking to increase that by about 50% to about 23 terawatts in the 2030. And we're expected to reach somewhere about 50 terawatts by 2100. Now, when I first came to the idea of looking at energy, I was looking at it from the point of view of what is the long-term availability of fossil fuels, what is the expected peak somewhere in the mid-century, and then what is up in this corner to sort of fill that gap, and what can provide that sort of capacity in the long run when you consider how massive our investment in fossil fuels is. I also became interested in the problem of climate change and what could get us to renewable, sustainable, greenhouse-free energy on the grid. And it's a very tall order to meet terawatts of energy when you look at what we've got today. We've got about 7/8 of our energy today is from fossil fuels. The future pretty much looks the same tomorrow if you look at the estimates. And by 2050, we're going to be growing in our total energy pie by about threefold. India, like the rest of the world, is racing for a better life that requires a great amount of energy. And if you this is from Václav Smil's Energy and World History, where he kind of says that if you're below about 100 kilograms of oil, you can't even meet the basic necessities of your citizens. Then you're in this phase of basic necessities. Once you can get to about 1,000 kilograms, then you see a noticeable improvement, and widespread affluence doesn't start until a little bit later on, and then you've got sort of this gold standard, and then you've got economies that aren't as productive per unit energy out in the far corner. Now, if you look at India's current energy situation, it pretty much looks like this. 57% of its commercial energy goes to electricity. And if you look at it capacity-wise, you see that it's dominated by coal, 51%, but it's actually much greater than that because the actual generation is some 66%. And if you look at, this was in the 2003-2004, but today in 2009, it really doesn't look any different in terms of capacity share. So what is India's energy strategy? Principally, they're working on, they've got 44% of their population without electricity. They have an all-time deficit of about 10%, a peak deficit of about 15%. They're 30% import dependent today. They're number 5 in the world greenhouse gas emissions at about 5.3%. greater than a gigaton of CO2 per annum. And they have 23 years of indigenous oil. The planning documents say 38 years of gas. I don't know how that squares with the new fines. And then they have 45 years of coal. Their strategy between now and 2032 is to grow primary energy by 3 to 4 times, electrical energy by 5 to 7 times. They're going to try, at least according to the scenario 11, to massively increase their share of renewables and nuclear to try to displace fossil fuels. So they have an extremely ambitious plan to do almost 5 times the amount of hydro they have to the full capacity, to expand nuclear some 20-fold, and to do a 40-fold increase in renewable. Now, if you were to, tell that, to the world, you'd think, wow, that's an amazing increase. They're going to beat it. But the problem is it gets so swallowed by the game. This is also sort of what it's going to look like between now and 2050 for the electrical. You'll be somewhere around 43% developed, roughly where China is in the 2032 time frame. And then by 2050, if you meet the DAE Paper 10 goals, you'll be very close to where France is. But the problem also for India is that even though our population is growing and they'll exceed China, they're also changing from a rural to an urban society. So the kind of power that you need for an urban society is different from the kind of power that you need when you think of yourself primarily as a village-based society. Unfortunately, if you look at the IEP's, the Integrated Energy Plan's projection, the future doesn't really look any different from today. The fact that growing that 3 to 4 times in primary power just swallows all those amazing inputs in renewables and nuclear. And this is despite the fact that coal is only going to be around for 45 years. You still have the majority share of your primary energy resource there. And emissions are going to be 4 to 6 times the present. So even after what I would term heroic efforts in hydro, renewable, and nuclear, India will be less energy secure in 2032 than it is today. It will be above 40% import dependent versus 30% today. It'll be less climate secure, putting out 4 to 6 times as much CO2, with coal accounting for some 66% of that. Even in 2050, coal still dominates, and that's particularly troublesome because, in point of fact, if you draw out the 45 years from the 2006, the entire indigenous coal within India disappears just short of the end of this chart. So what do you do to replace 46% of your capacity and 49% of your generation? Particularly when you've got groups like the Energy Watch Group saying coal may peak at only 30% above its current level, and India is projecting to need some 3 to 4 times that. Even here, where it's a slightly smaller, some 300 gigawatts of capacity is still built on coal as far out. So the problem is that at least by 2032, hydro and nuclear together can't exceed 8 to 10% of commercial energy supply. And with a 40-time increase in renewable energy, it's only about 5 to 6% of India's commercial energy. And while thorium and solar may provide something beyond 2050, that needs to be promoted now. And of course, I talked about the import dependence. The other problem is capacity addition. An earlier article this year said that India had fallen 70% short of its capacity addition goals. So whether or not it can even make those is in question. Now, turning to the problem of climate change, as I understand the goal is to try to stay below 550 parts per million and try to stay above this level of pre-industrial. Now, the world right now is putting out about a little over 8.38 gigatons of carbon per year, which is about 30.75 gigatons of CO2 per year, and it's growing at about 3% per year. So obviously, if we're going to try to flatten that out, there are a number of things that we have to do to try to do that, and this is from Marty Hoffertz. Basically, the thing is that and I've got a slide that's a little clearer about this, but what the article here says is that if you want to do that, you have to make massive investments in carbon-free power, and that there are no energy systems technologically ready today to achieve those large amounts of power. So this is a fairly clear graph. This is the projected total energy needs of the world going up to about 50 terawatts in 2100. And this is the curve that you would need to do to make the emissions. And what this shows basically is that of the 50 terawatts you're going to need in 2100, no more than 10 terawatts can be from fossil energy sources. So 40 terawatts, when we're only using about 17 today of all forms of energy, is going to be required. So this is an amazing amount of energy if you hope to meet development goals. And people like Mike Sneed, who've talked about the end of easy energy and what to do about it, They say if I take most of the advocates at what they say they can do, there's still a very significant shortfall in the 2100 time frame. So you'd like to have an energy option that is clean, safe, reliable, and particularly that can be useful for baseload energy. And if you look at what's available in the renewable energy sources and try to add it up to 55 terawatts, really the only big number is solar. But the question, of course, is, how do you get at it? So what if there was a renewable carbon neutral energy source that was baseload appropriate and scalable to meet that full 50 terawatts? Wouldn't that be interesting? So this is the space solar power satellite that I showed you, and I'm going to talk a little bit about it. So of course the sun puts out this amazing amount of energy, and today the Earth needs a little in excess of 15 terawatts, but what's the best way to harvest it? Well, of that, a bunch is incident upon the Earth's surface, but the Earth has this interesting design flaw from the prospect of a solar engineer. It rotates. And because it rotates, it means that you've only got about a 20% duty factor on the solar cell, and that decreases its real efficiency in terms of being able to take the sun's energy and put it in. So while it may, in a nice location on the ground on a non-cloudy day, get 1,000 watts per meter squared, at night it's getting nothing. Now, an equivalent solar cell in space is getting 1366 watts per meter squared. Now, this also is reduced by seasons in temperate climates. Then you've got weather cycles, so that rather than getting 1366, you're getting somewhere between 125 and 375. Now, space solar power is an attempt to break the tyranny of these cycles, not through storage or distribution, but by changing the collection point. So the idea is to go where there is no light, where there is no night. If you get high enough above the Earth, you're not in the shadow of the Earth, at least for about 99% of the time. So on the ground, you are in a period of darkness for a long time, and then you have a up and then a down. But if I move that same solar cell up into space, I collect a lot more flux for that same area. And seasonally, the same thing. So this is a temperate zone, and you can see that this is the summer curve of the insolation, solar energy available, and then this is the curve in the wintertime, and then this is what you'd be getting off of the same square meter of energy. Now, when you talk about how much land you actually need on the ground, well, it depends a great deal on whether or not you're really trying to solve the whole problem of base load. And if you're thinking you can't supplement it in the long term with these fossil fuel energy sources, then it becomes a much more interesting problem. Because if I need this much area in space, just going through the atmosphere, I lose this much, I need that much more. If I include the day-night cycle, I need this much. If I take the case where I have to at least be able to supply 5 weather days of overcast days, then I have to have a certain level of overcapacity. And if I include storage too, then I have to way overbuild. So, it does become a question of how much do you really have to overbuild to be able to assure that you can get power for a 24-hour society. Another thing from New Scientist showing the same thing. So basically the way the satellite works is you have these large collectors that focus it onto some kind of energy conversion. There are thin film ideas that I'll show you later on, but this is the most typical design. Then you convert it to DC, then you convert it to some type of RF. In this case, it goes to what's called a rectifying array. These are fairly large things, about the size of a municipal airport, but the land, because it's very efficient in the biosphere of converting back to energy greater than 80%, and because it's quite transparent to sunlight, it's thought that you would be able to use this for dual use for agriculture and pastoral purposes. Now, the beam itself is fairly similar in frequency to things that we carry around with us today. It's done in a frequency that's pretty much transparent to the atmosphere, where you've got less than 2% losses. And then it's long frequency non-ionizing radiation, so it's not something that's going to cause you cancer. And the amazing thing about it is, because I am using constant energy over the entire time, rather than just having it peaking and going away, I can actually, and because I'm converting it at a much higher level of efficiency than I can with a solar cell, that I actually can have a much more productive energy per unit land with a much lower incident beam. So I can be beaming at about the 1/6 the intensity of sunlight in the center of this Gaussian and still be getting more energy out per unit land. So the significance of the concept is that you could have 24-hour baseload appropriate power, urban appropriate, that could displace coal, that could reduce concerns about nuclear proliferation, or certainly supplement nuclear, since we're going to need to scale up to that. Now, how scalable is it? Well, just if you were to take this band where we put our communication satellites and arbitrarily make it a kilometer wide just for scaling, you have about 212 terawatt years of power passing through that. And the actual exploitable slots that have been calculated are somewhere above 177,000 terawatts that you could actually put up there. Now that's in excess of 3 times what humanity needs for all forms of energy at the end of 2100. And of course the thing is, this has been calculated by a couple of Japanese authors, that very similarly to nuclear, the life cycle CO2 production of the satellite, including launch, is some 60 times better than coal. So it appears to have a number of favorable environmental traits. One is that heat rejection to the biosphere would be less even than solar, because for the same land area, even assuming you could get to, say, 50% efficient solar cells, you're still rejecting 50% of that heat to the biosphere. Most of the inefficiency in this system is out in space, and within the biosphere you have some 80+% efficiency. The other thing is I already talked about the CO2 emissions. Energy payback time, because you have such high flux, appears very equivalent to terrestrial solar. And then water usage is negligible. So places that you can't put a nuclear power plant, like a desert, become attractive for something like this. And then, of course, the land usage is considerably more attractive. So in terms of India's own conception of what is suitable in their planning documents, it's scalable. Its environmental impact seems quite good, with less land, less water, less CO2. Its security of the source, depending on how you define it, certainly the sun's going to last for 1 billion years. That's a few orders of magnitude longer even than nuclear. So you could say that it's over 1 million times more secure than any fuel. Because it's manufactured power, you don't have the same kind of market risks. Of course, the technical risk is substantial, and the cost is something that would require a program to address. The drawbacks are, of course, its low state of maturity, and that the business models depend on multiple significant technical successes. And, of course, its relative obscurity. There are significant unknowns. At the moment, there's no universal agreement on the best satellite design or the best launch methodology to get there. I will say, though, that from our multiple meetings with NRL and AFRL, it's very clear that there's no lack of ideas to get you to the kind of low-cost launch you need that aren't attractive if you don't have a large market like this. It just doesn't make sense to go after the kind of low-cost launch if you're only launching to space about 10 times a year. So the state of maturity right now for this is it's obviously pre-commercial, pre-pilot, pre-demonstration, but it's well understood science and components, subcomponents, and that's important. I mean, essentially you're talking about solar cells and radar components. And so it's in a very different category than something like fusion, where there are many, many different unresolved questions that have to be answered. And it's considered engineering ready within the aerospace community. So a useful analogy is sort of a hydroelectric dam, very high capital costs, long payback, no fossil fuel feed, completely renewable, and also very large in scale. Typically you're talking about 1 to 10 gigawatts in size. A number of very interesting trade space and architectural choices that are out there, even though the field is quite small. And if you're interested in space, this really is the killer application, because this is from Ivan Becky, the former head of Advanced Concepts. This line is the launch to orbit mass for space solar power satellites, and you can see that on a logarithmic scale it dwarfs everything else that might possibly be there. So lots changed in the technology since it was last looked at, in materials, in directed energy, in robotics and in space, construction, deployable and gossamer structures, thermal protection, and tethers. So when this was last seriously looked at 3 decades ago in 1977, solar power efficiency was only 10%, and you heard where it is today. Solid-state amplifiers were very low in efficiency. It required a mechanical gimbaled array. Now we're talking about electronic beam steering. The power management requirements were exceptionally high. That posed a lot of problems. The launch requirements required an unbelievably large launch vehicle of some 250 tons. Now the modular designs look like they may be down in the 25 tons. We were nowhere in terms of space robotics and automatic assembly, and so that makes a huge difference as well. This is sort of the 1978 reference design that DOE and NASA looked at. This was the later one of circa 2000. And then these are the more modern ones. So wireless power transfer has been demonstrated. You look for windows in the atmosphere. And of course, I'm not the only one who has expressed an interest. I'm in India because Dr. Kalam gave a speech at Boston University laying this out. Mitsubishi, JAXA, METI, and 16 companies have announced a $21 billion or 2 trillion yen project to realize a 1 gigawatt commercial by 2030. PG&E has talked about an interest in it with a company called SolarN. They're one of some 6 companies specifically interested in this. AESI in India is quite interested, and of course the Pentagon came out with several reports, of which that was the first on it, and it's supported by a number of others. Even the Department of Commerce has a web page, and some have suggested India and U.S. cooperate on it. So that's it.